In this video, I'm going to show you an example of how they handle chemical risk assessments when the chemicals are intentionally added to the food. Here's a basic summary of how you do that. If somebody's developing a new food additive, something to enhance flavor or to preserve the food or to make it easier to handle, whatever reasons that they may do that, if they're inventing a new one, they have to do some toxicological studies before the Food and Drug Administration will approve the use of that chemical. So if no one has undertaken those toxicological studies, you have to do it. If they've already been done, then you can just use the results of what's out there in the literature. So using that toxicology, you would determine a no observed adverse effect level. This is basically the largest dose of this chemical that a person could consume every day for the rest of their life and have no adverse health effects. Because that NOAL is developed based on animal data in almost all cases, we have to get from animal to humans, and we use safety factors, sometimes called an uncertainty factor, to do that. When you have the NOAL and a safety factor, you can calculate the ADI, the acceptable daily intake, and then you would begin to calculate the EDI, the estimated daily intake, what people actually do consume, and then compare those two numbers in a simple ratio or fraction. So here's how we begin. The toxicity is done with animal studies. Usually you give relatively high doses to relatively few animals, and if you see adverse health effects, you say, uh-oh, that's too much, so let's try a smaller dose. And then you give a smaller dose to some animals, and if they're still showing adverse health effects, you say, uh-oh, that's too much. And you keep lowering the dose until you get to a dose that causes no adverse health effects in the animals. We already talked about dose response curves. These chemicals, because they are intentionally added, we tend to use a different approach, the acceptable daily intake. The acceptable daily intake relies on this concept here, the NOAL. It's the biggest dose of a chemical that produces no toxicity, okay, or the highest dose at which no adverse effect is observed. The trick, though, is you got to go from a NOAL developed with animal data to humans. And for the human, we don't use a NOAL, we use an ADI, an acceptable daily intake. So there are two extrapolation problems. Actually, there may be many more, but there are two primary ones. First, we're going from animals to humans. And second, all of those animal tests were usually done at very high doses, and humans are usually exposed to very low doses. So there are lots of mathematical models can do that in the dose response curve. When you have lots of data points, you can develop a dose response curve. But there's an alternative approach, and that is to use safety factors or uncertainty factors. And the way that would work basically is you get the NOAL, as you see at the bottom of the screen, and you would divide it by a safety factor. To get a safety factor, you're going to multiply all the factors that pertain to a particular assessment. So here's an example of what you might do. You might say, okay, well, we'll use a 10 because we're extrapolating from animals to humans. And we'll use a 10 because there's variability in the population. And we'll use another 10 because this can affect children. So that's 3 tens. We would say 10 times 10 times 10. That's 10 to the third or 1,000. And we have a safety factor of 1,000. So in that case, you would divide the NOAL by 1,000. That would produce something called the ADI. This is the maximum acceptable daily intake. It's not an absolute limit. That means if you happen to exceed it on a particular day, that doesn't mean that you will develop a cancer or any other kind of health effect. But it's an amount that can be consumed daily for a lifetime without adverse effects. This is a population number, not an individual safety number. And when we say that, we mean this doesn't really account for people who might be hypersensitive to certain chemicals and such. After you figure out what's acceptable, you have to figure out what people are really doing, and that's estimating the daily intake, or the EDI. So you get information on the concentration of the chemicals of interest. You would use consumer surveys to estimate the portion sizes that they consume and how often they do that. You might have some assumptions that you would use, but all this stuff together would be used to calculate an EDI, and that can be cumulative. So here's how it would work. The ADI is defined up above. So we would have toxicity studies that would lead us to believe that 5 milligrams per kilogram daily for a lifetime is producing no observed adverse effects. In this case, assume we have a safety factor of 100, so 5 divided by 100 is 0.05, and that's the ADI. That's a bright line, so to speak. If you have an EDI below this, that's considered safe, and an EDI above this is considered less safe. And so that's how chemical risk assessments work when we have additives that are put into food intentionally. If you would have an additive that would be above, then there would be regulations. You might do something to require the manufacturer to limit the amount that's put into a product, and so on. So when it comes to risk management, you're usually doing this kind of assessment we looked at for an additive, something that's intentionally put in, and the manufacturer is required to keep the EDI under the ADI. So you do a cumulative analysis looking at all the foods, usually by doing a conservative assumption. So for example, when they do something like this for aspartame or sucralose, they would make an assumption that, let's assume that all the sweetener in a person's diet comes from aspartame. And they would estimate what that level of aspartame would be. And then they would compare that to the ADI. Or if we had another chemical, maybe something that was a color fastener that went into packaging material, they would assume that all of that chemical migrates into the food to find out if that was so, would that be enough to cause a problem. So cumulative impacts are usually covered by conservative assumptions. So this and the little Exxon video would give you an idea of how chemicals are handled in foods.